Hello everyone. Thanks for taking the time to attend this talk. My name is Swati Sehgal and I'm a senior software engineer and work for Telco 5G Compute team in Red Hat. My team and I have been working on enhancing Kubernetes and OpenShift to deliver leading-edge solutions and innovative enhancements across the stack. Our goal is to enable customers and partners to run high throughput and latency sensitive cloud native networking functions on OpenShift. I've been working with a number of engineers from Red Hat, Huawei, Nokia, Samsung, and Intel with the goal to enable topology-aware scheduling in Kubernetes. And today I'm here to talk about the work we've done on this project so far. So let's dive in and look at the agenda for today. I'm going to be talking about hardware topology and why NUMA alignment is important and why it is needed. How NUMA alignment can be achieved in Kubernetes. We are going to discuss topology unawareness of Kubernetes default scheduler, how the Kubernetes default scheduler works. We'll touch on the key components of topology-aware scheduling, end-to-end proposed solution, the current status, use cases, and references. So let's look at the first item. Topology, hardware topology. What is NUMA and why NUMA alignment is important? NUMA stands for Non-Uniform Memory Access. It's a technology on multi-CPU systems that allow different CPUs to access different parts of the memory at different speeds. Any memory directly connected to a CPU is considered local to the CPU and can be accessed very fast, as opposed to any memory not directly connected to a CPU, which is considered non-local. Now, on modern systems, the idea of having local versus non-local memory can be extended to peripheral devices such as NICs and GPUs. All memory on NUMA systems is divided into a set of NUMA nodes, with each node representing the local memory for a set of CPUs or devices. For example, in this figure, we have CPU cores 0 to 3 and devices connected to PCIe bus 0. Those would be part of NUMA node 0, whereas CPUs that are from CPUs 4 to 7 and devices that are connected to PCI bus 1 are part of NUMA node 1. This example shows us kind of a one-to-one mapping of NUMA nodes to a socket. This is not necessarily true. There can be multi-socket systems where multiple sockets are on the single NUMA node, or individual CPU devices of a single socket may be connected to a different NUMA node. So now let's move into why NUMA alignment is important. For performance sensitive applications in the field of telco 5G, machine learning, AI, data analytics, CPUs and devices should be allocated such that they have access to the same local memory. Another example is DPDK-based networking applications that require resources from the same NUMA node for optimum performance. How do we achieve NUMA alignment in Kubernetes? At a node level, Topology Manager which is a kubelet component, is responsible for coordinating the topology of resource allocation of CPU and devices. It has a set of node level policies, for example, best effort, restricted, single NUMA node, and scope to define whether you want resource alignment to happen at a pod level or a container level. It basically orchestrates CPU manager, device manager, and the upcoming feature memory manager by gathering hints from them and using those along with the policies to align resources, allowing workloads to run in an environment optimized for low latency. In order to illustrate and understand what NUMA alignment and not non-aligned resources would mean, let's consider a simple example where we have one SRV device or SRV virtual function. We have two CPUs and some huge pages. So that's the set a workload is requesting. So a scenario where the resources are not aligned would look something like this, where these CPUs are kind of split across the different NUMA nodes. And then another scenario is this, where resources are NUMA aligned and the overall performance of this application would be much better. Now, we've talked about topology managers taking care of resource alignment. So, what is the challenge here? Why are we it's still saying that there is a gap that needs to be filled. So let's talk about that a bit. Topology unawareness of default scheduler is the challenge here. Despite the introduction of Topology Manager enabling topology alignment of requested resources, the scheduler's lack of knowledge of resource topology can lead to unpredictable application performance, in general, underperformance, and in the worst case, complete mismatch of resource request and kubelet policy. The scheduling, it ends up scheduling a pod where it's destined to fail, potentially entering into a topology affinity error failure loop. Let's try to understand this a bit better. So here I have two nodes with 80 CPUs and 8 devices split equally across NUMA nodes. In this case, both the nodes have been configured with single NUMA node policy. So in this case, the workloads, so for example, if I have a bunch of workloads that are deployed on this cluster, um, and if they're distributed differently, but the cumulative resource consumption and hence the allocatable resources on each node appears to be the same, which is the case here that you see here. So we see that um, there are four instances of device A on both the nodes available and 76 CPUs that are available on both the nodes. So from scheduler's point of view, it sees both the nodes as exactly the same. It's from especially from a resource point of view. So when a pod that's requesting four instances of device A and four CPUs, from scheduler's point of view, it's a completely valid decision, and it finds worker one as a perfectly valid candidate for scheduling the pod. However, because the topology manager has been configured with single NUMA node policy, it will not be able to align the resources on the single NUMA node because it's requesting for four instances of device A and we don't have four instances of device A on just one NUMA node. And hence this pod would end up in being in topology affinity error. So how does the default scheduler, the Kubernetes default scheduler work? Let's try to understand that. So we have this pod specification file. Here the pod is requesting a bunch of resources. The request goes to the API server. The scheduler is essentially a control loop that looks for unbound pods. And in this case, this pod is unbound, so it runs a set of rules, algorithms to identify a suitable node for this pod. Um, and basically, it binds the pod, which means that in the pod spec, it just writes that now this pod has been assigned to this node. So from there on, it's a responsibility of the kubelet or of that is running on the node where the pod has been assigned. So kubelet is responsible for resource allocation. Topology manager is part of kubelet, so it calculates the hints, tries to align the resources, and there could be two cases here. Topology manager, which is essentially an admit handler, could admit the pod, and pod is able to is allocated all the resources that it needs and is up and running and all good to go. Alternatively, it could get rejected in scenarios that it is not, the policy does not meet the available resources, and the pod ends up being in topology affinity error. So when the pod is successfully scheduled, um, the pod object and the node object gets updated in the API server and etcd. Whereas in scenarios where it's rejected, it just ends up being in a topology affinity error. If it's part of a deployment, the pod constantly, there's a series of pods that get created because the scheduler tries to keeps scheduling the pod on the same node, and essentially that's the biggest challenge here that we are trying to solve. Hmm. So, so in order to optimize the cluster-wide performance of the workloads, resource utilization, and enhance the overall system as a whole, the scheduler needs to be enhanced to increase the likelihood of the pod to land on a node where it will fit. And so we've taken a few steps and we've proposed a few changes in order to enable the scheduler to be able to do that. So one of the thing is that the scheduler doesn't have that visibility. So how do we expose that to the scheduler? And how do we gather that information first? And then how like we need changes to the scheduler itself to be able to make the decision based on the newly gathered information, for example. So the key components that we've proposed are Pod Resource API, Node Feature Discovery, Topology-aware Scheduler plugin, Node Resource Topology API. So let me give a brief overview of each of these components, and then we can talk about how these components stitch together to form a proper end-to-end working solution. So Pod Resource API, it's a kubelet endpoint for pod resource assignment. Pod Resource API was so we identified a few gaps and we proposed a few enhancements to add, for example, to add support for CPU IDs and device topology. In addition, we also proposed get allocatable resource and watch endpoint to be able to gather information of the available and allocatable resources of the node, and watch endpoint is for gathering information in an event-based mechanism where, say, a pod is scheduled, and now you need to have the information as to how the resources have been allocated or modified, and in order to account them properly. The next piece, the second one, is node feature discovery. Initially, we started working with a completely different component. We called it Resource Topology Exporter, and it was a daemon set that ran on all the nodes in the cluster, gathered the resource information by accessing the pod resource API, and then created CRDs. But then when we proposed this and brought it to the community, especially Signode, they recommended that we should look into NFD. NFD is already a node fleecing agent which exposes hardware capability in the form of node labels, annotations, and extended resources. So exposing hardware topology information as CRD is a natural next step. Excuse me. So the third piece is Topology-aware scheduler plugin, which is the most important piece. So this is the component that uses the CRDs that have been created by Node Feature Discovery to make a NOMA-aware placement decision. So Um, like I mentioned, node feature discovery, it basically runs as a daemon set, runs on all the nodes, gathers information on what are the resources that have been allocated, what are the resources available, and then we have to have that information in terms of have the granularity of resources per NUMA node so the scheduler can make a proper intelligent decision. The fourth component is Node Resource Topology API. It is a CRD API used by NFD and Scheduler plugin. It acts as the glue between them, and we are in the process of figuring out where do we house this API. So now let's talk about the end-to-end solution. How these key components and the pieces fit together to actually have to enable topology-aware scheduling in Kubernetes. So kind of similar to the diagram I showed you earlier when I was showing the working of default scheduler in Kubernetes. Now we have NFD, which accesses the pod resource API endpoint and populates CRDs. The scheduler plugin uses the CRDs that are created per node to make topology-aware scheduling decision. Sorry. Um, so again, we have a pod with resources that's requesting a bunch of resources. The request goes to the API server. Pod looks at or unbound pods, and now it has the information that it did not have previously. It has information, it looks at the CRDs corresponding to each of the node in the cluster and uses that to make a topology-aware scheduling function, uh, topology-aware scheduling decision. So here what we do is the scheduler plugin essentially is a simplified version of Topology Manager, and it tries to determine how can I make sure, based on the policy that is configured on that node, I can align the resources based on the request it's making. And once the scheduler does its part, it binds the pod to a node. It's again the responsibility of kubelet, which does its resource allocation. And then we have to do an additional step, which essentially is taken care of by NFD because it's running like an instance of NFD would be running on the node, and it would update the node resource topology CRD corresponding to that node because now some resources have been kind of taken away from the node, so we need to account for that. So yeah, so let's see diagrammatically how things have changed. So this was default scheduler's view. Both the nodes look exactly the same. We don't have visibility into what NUMA nodes those resources are from, and ended up leading to topology affinity error, or the possibility of leading into topology affinity error. So now with topology aware scheduler, the view is more granular. Now we have visibility into resources at a NUMA node level. For example, on worker 0, NUMA node 0, we have no devices available and 70 or sorry 36 CPUs available. On NUMA node 1, we have 4 devices available and 40 CPUs. And then on worker 1, we have 2 devices available on both the NUMA nodes and 38 CPUs on both the NUMA nodes. So now the view is more granular, which enables it to make the intelligent decision. So again, when a similar pod request comes in for requesting 4 instances of devices and 4 CPUs, it is able to place it on the right node. And let's look at the current status. So we've um, like over the course of time we've been working on this project, we've identified a few gaps. So one of them was changes to Pod Resource API. So we proposed a few enhancements to Pod Resource API, which got merged. Earlier, it just used to look into or account for devices, and um, uh, now we have proposed device topology information as well as CPU ID information as part of the Pod Resource API. So that change was merged. In addition to that, we have get allocatable resource and watch endpoint, which we are targeting for Kubernetes 1.21 release. Node feature discovery, as I mentioned, it started as resource topology exporter. We have kind of code and the enhancement proposal corresponding to that. So you can have a look. And then we have the NFD development work, which is currently in progress. I have a demo there which showcases NFD running and it creating CRDs, as well as like the issue and the proposal doc for you for anyone who's interested. The third piece, Topology-aware scheduler plugin, we have again a Kubernetes enhancement proposal corresponding to the scheduler plugin and the code. So feel free to play around with it. And the last but not the least, in fact, that's one of the most important things right now, is Node Resource Topology API. As I mentioned, it's a glue between the Topology-aware scheduler plugin and NFD. We need to figure out where we are going to place it. We have a PR there, placing it in Kubernetes staging, but we need to kind of figure out with the community by showcasing the value proposition of topology-aware scheduling natively in Kubernetes to be able to successfully place it in staging. So use cases. So as I mentioned that I've been working with stakeholders and contributors from various organizations who've been contributing and supporting this work. There are a few use cases that actually have come from them, and that just totally aligns with the idea and the reason we are proposing topology-aware scheduling. So we have VRAN user plane use case by Nokia, where packets need to be processed with extremely high bandwidth. Pods handling the user traffic require SRVVFs, huge pages, and CPU resources from the same NUMA node. Due to failover requirements, the scheduling of the pod has to be reliable. Then the other piece is containerized 5G deployments and multi-access edge computing to basically deliver low latency access to edge applications. And then the third one is cloud native networking function, a cluster at a cluster level. So one of the things that was very interesting was until this point we had been looking at full resource alignment, but an important piece is what if a workload just needs partial resource alignment? Like it requests for a resource, but it's okay if two of those resources are on the same NUMA node, but the third one is not. So scenarios like that are is another use case that we would in the near future like to address. GPU direct scheduling use case by Viasat, which requires direct GPU to NIC transfer over PCIe instead of going through CPUs. So, like for detailed information for these use cases, uh, and and actually a little more than that I've been able to capture here, please refer to the use case doc that I've linked here. In this document, you'll find NVIDIA's very interesting way of preventing topology affinity error, and I'd highly recommend you read through it. Just it gives you an insight into uh, what all you need to do to be able to avoid this error, and they've done it in a brilliant way. But it's just a really nice read. Okay, um, so so yeah, the last piece is kind of pointers for everyone. This this project itself has a lot of information to digest, so um, here are links for some people. Um, we have we have demos as well that I've linked here, showing like topology aware scheduling with resource topology exporter, which was our initial implementation. Then NFD exposing CRDs. I have a summary doc where you'd find all the links that you need for for this particular project. Anyone who wants to get started on this would be able to kind of get up and running by looking at the doc, because obviously there's a lot of information. The use case doc, which I mentioned. Last but not the least, if anyone who's interested in getting in touch and contributing to this project, we have a Kubernetes Slack channel. We call it Topology-aware scheduling. So feel free to ping us. My email address is there on the screen. If you want to email me and want to get a copy of the slide deck, I'd be more than happy to share it with you. Um, Thank you so much. I think that finishes off my presentation. Thank you.